Okay, hello everyone. Thank you for your patience as we try to sort out some technical problems here. And yeah, welcome everyone to the first seminar session of the AGU Atmospheric Science Early Career Committee for 2025. My name is Christian Lackner. I'm part of the seminar subcommittee, and we also have Claire, Wenhao, Yuan Yu, and Yuhan from the subcommittee here today. As the Early Career Committee, we provide resources and create and promote professional activities for early career scientists. Announcements from the committee, for example, on upcoming events will be made in the AGU Atmospheric Science section newsletter and on the committee's Instagram page. If you're interested in presenting at this seminar series, you can submit an abstract with the QR code on the left. The Early Career Seminar Series is a great opportunity for graduate students and early career scientists to showcase their work and to create potential new collaborations and networks. It is similar to an invited talk that you can include in your CV. We also welcome any feedback on today's seminar that you can provide with the QR code on the right. And we'll also put these links in the chat so you can access them until the end of the seminar. And please note that this seminar is being recorded and the recordings will be provided on the AGU website. With that, I would like to introduce today's moderator, Dr. Meiyun Lin. Dr. Lin earned her PhD from the University of Tokyo in 2008. Currently, she's a research scientist at NOAA's Geophysical Fluid Dynamics Laboratory, where she leads development of the Variable Resolution Global Chemistry Climate Model. Her research focuses on Earth system processes and biosphere-atmosphere interactions during high-impact extreme events, reductions in ozone removal, and increases in wildfire and dust emissions. Yeah, and with that, I'll hand it over to Meiyun. Yeah, you can go ahead.
Okay, thank you, Christian, for the introduction. So, and thank you everyone for tuning in for today's seminar. And the theme of today's seminar is global climate and air quality implications of regional emission shift, which is a very important topic. And we have 3 early career speakers lined up. So each speaker will give a 15 minutes presentation, 30 minutes presentation, 2 minutes for questions. And I think after all 3 speakers have given their talk, we also have some time for Q&A section. So if you did not get a chance to ask the question earlier, please ask question at the end of the all 3 talks. So the first speaker is Dr. Mahendar Rajwar. He is a postdoc researcher at the National Institute for Environmental Studies, NIST, in Japan. And his primary research interest lies in the observations of ozone precursors and assessing their role in ozone pollution. And with that, so I will, without further ado, let's welcome Dr. Mahendar Rajwar.
Thank you so much, Megan. And I'm a, oh. My slides are visible to all?
Yes.
Yeah, okay.
Yeah.
So okay. So thank you so much for the ASU Atmospheric Science Early Career Seminar Committee to providing me this platform to express and present my work in front of you. So today I'm Mahendar Rajwar, and I'm currently in the NIST, but in the past I'm from India, Aries, Nainital, and for where I did this work, and I recently joined NIST in April. So today I'm going to talk about the hydrocarbon chemistry and their observations, the perspective over the central Himalaya and the associated the IGP regions, some of the regions, and their roles in the ozone formation and other secondary formation processes. So let's start with the non-methane hydrocarbons. So basically, non-methane hydrocarbons are the subclasses of the volatile organic compounds. They are primary air pollutants and they are also have the very much important role in the secondary organic aerosol formation and the tropospheric or surface ozone formation. So you can see this is a cartoon diagram which can say in which area the hydrocarbon is affects the atmosphere. It's basically emitted from the natural and anthropogenic sources in the atmosphere. It transform into the ozone aerosols and also implemented into this in some health risk also. So if you see the ozone chemistry with the non-methane hydrocarbon in general form, in the ozone formation in the troposphere mainly governed by the production of the one atomic oxygen, and by this atomic oxygen combined with the oxygen molecule transform into the ozone molecule. Whereas if in case of the non-methane presence of the non-methane hydrocarbon in the atmosphere, the oxidation of hydrocarbons forms the HO2 and RO2, that is a hydrogen peroxide, and there is a two different pathway to formation of ozone, and there is a, you can see one is a very straightforward which is very well known pathway, and second one is the one additional steps is there. So we got n numbers of the ozone molecule, where is the n represent the number of the ozone molecule which is corresponding to the number of the carbon atoms present in the that hydrocarbons. So basically this is the some symmetric diagram to show how the hydrocarbons presence of the hydrocarbon influence the ozone formation in the atmosphere. So you can see the red plot. This is basically the without non-methane hydrocarbons. So there is the production is much lower as compared to the atmosphere where we have the hydrocarbons. So is this and another, this is isoplate diagram. So you can in the isoplate diagram also you can see whenever there is a only high number of the NOx, then we only not get that much amount of the ozone production as when we have non-methane hydrocarbon in our air. So in about also ozone formation potential or ozone formation production efficiency of the non-methane hydrocarbon is much higher than the other primary precursors. So if you think about yes, if you think about the different atmosphere, so it is, you can see in the different atmosphere that ozone formation rates are the different. So these stay solid line represent the ozone formation rates. So you can see in different atmosphere, the urban, rural, and marine. So there is a different ozone formation regime, and the rate and their values are also different, and you can see the formation of ozone is not that much straightforward. It's non-linear in the nature. That means if you it's not directly depend on the NOx or hydrocarbon concentration on linear basis. And if you see their observations over the Indian perspective, it is very limited, and where there are very few sites in the Indian subcontinent where we have good number of the hydrocarbon observations and NOx observations simultaneously. So you can see in the Himalayan region that there is only one side, which is the side from where we have the present observations. Only this show the picture of the Himalayan region. So if we go further, so these are the some observation sites, and in the Himalayan region and IGP region. So we choose one side is the IGP side, and another side is the mountain side, so that we can see some inflow flux over the Himalayan region, and see what kind of the properties or the what kind of the processes which governs their labels, hydrocarbons label at the mountain side. So we also try to collect some ozone observations, surface ozone observations, to see the role of non-methane hydrocarbon in surface ozone formation. So let's start with some great results. So you can see these are some diurnal variations. So you can see that there is a very specific type of the diurnal variation where we have the daytime buildup, which is more something is a very much contrast with the urban behavior, because in urban behavior we have the early morning and the evening time peak. So from here what we can take the message that whenever we observe at the mountain side with the convective boundary layer evaluation and the upslope bends, the pollutants from the IGP it's coming to the that mountain side, and these are the some first time results we have uh, got. And if you see the monthly picture or the seasonal picture of these non-methane hydrocarbons, so you can see the springtime higher values, and also the monsoon time lower values, which is means springtime there is so many biomass burning, forest fire, and other combustion related processes which governs their higher levels of these non-methane hydrocarbons. Apart from there are few hydrocarbons which do not show any kind of the seasonal variability. There is not that much influence from their sources and the different seasons. So whenever we see the hydrocarbons in the mountain side, the present mountain side, the ethane is the most dominated one, and propylene and the ibutane are least dominated. So the once we check, we also got that the role of the IGP is much, and biomass burning is much dominated at over the mountain side. And once we compare our results with the another IGP site, so what we found, the labels are quite low. It's well known that is the IGP is much polluted. That's red color bars showing the IGP labels, and this black color bars showing the mountain sites in the Himalayan region. So you can see very much, very less amount labels of the non-methane hydrocarbons at the mountain side. And if you see their compositional picture, so you can see the ethane is much dominated at the mountain side, whereas if you see the propane is dominated at the IGP regions side. So where is the IGP region side? If you see, the propane is one of the major emitter from the LPG emissions. So we also try to look in this matter. So apart from that, we also try to replicate, see which non-methane hydrocarbons have the more ozone formation potential or have the more ozone formation regime. So we also try to simulate some box model results. So and also did some that sensitivity analysis. So this is a left side figure is showing the variability of the ozone with respect to the NOx level, and right side of the plot showing the variability of the ozone with respect to the non-methane hydrocarbons. But however, we can see in the NOx cases, the variability is quite high. The variations is much more. Increment is much large as compared to the hydrocarbons changes. So what we can say that it is more likely the most the ozone labels are the more contributed to the NOx sensitive regime. And if you see, we also try to find out how much ozone is photochemically produced. For this, we also did the calculation and found that we have some about 49 ppbs of the ozone production during this daytime period, and out of which the 8 ppb of ozone is lost, and the total we have the production is the 41 ppb, about 41 ppb of ozone. And once we subtract this box model, the box model production and the real time production of from the observations, what we found some little bit amount of the ozone, which is governed by the transportation and other dynamic processes over this region. We also quantify the role of different equations, chemical equations over the ozone formation, and it is well known that HO2 plus NO is most dominated reaction over this region. And apart from that, we also try to figure out which non-methane hydrocarbons are more dominated by the left side figure is what we simulated from the box model, whereas the right side figure is represented by the observation. So you can see in both the figures we have the quite good amount of ozone in case of the aromatic hydrocarbon, which is benzene, toluene, xylene, etc. So you can see this they have the most dominant highest ozone formation potential or rate as compared to the other hydrocarbons, which also reconfirmed in the observations also. Apart from that, very now in 2024 we have a chance to do a mobile laboratory campaign. So we have started from the Strangle, the Himalayan regions, to this urban, very much urban Delhi, the one of the most the Indian capital, that is Delhi. And so you can see this is a land cover land use, so it's very urbanized uh, site is in Delhi. So we started from Nainital, we and do the collection of the ozone hydrocarbons simultaneously. And what we observe some this kind of the results. So you can see the with the because in the winters we have lot of the fog and etc, so we want to see whether how the ozone hydrocarbons are behaving during the season. So we try to sample out, and so what we see, one interesting feature, if you see the during the foggy days we have less number of ozone as compared to the uh, normal days, where if you see the ozone, the foothills ozone labels, it quite showing the seeing that during the normal days the levels are quite high as compared to the in the foggy day. In the foggy day what happens, so this can be due to the higher level of the NO in the foothills as compared to the other regions during that. So NO is going to kill that ozone, and this depletion is happened in the absence of lesser in the presence of the less solar radiations. So we also try to figure out some hydrocarbon behaviors, their profiles at the different sites. So Delhi NCR regions show much higher values as compared to the other regions. Whereas if you go to the Himalayan foothill sites, the numbers is again increases. So it means it's the high Himalayan one is the Himalayan region is also acts as a barrier for the dispersion of these pollutants, as well as if you see the foothills region is the quite high number of hydrocarbons, which also transported to the higher Himalayan regions. And we also try to
And
figure
then
out.
Mahendar, sorry to interrupt.
Yeah,
You
yeah,
have 30 seconds to wrap up.
yeah, last slide, sorry.
Okay.
We also try to figure out the hydrocarbons and their ozone formation potential. So you can see Delhi NCR region is a much more higher ozone formation potential as compared to their foothill side. So at last, I will acknowledge my supervisor, Director Arij, and Arij team with whom I did this work. And this is the picture where I took some hydrocarbon sample. Is very a very known peak in front of the Panchachuli peak. And thank you so much for the attention. Any question? I'm happy to answer questions.
Okay, so now we open the floor for questions for 2 minutes. Are there any questions? I'm hearing none. So I have a question, Mahendar. And so since this is a high elevation site, and I wonder, have you looked into the influence of stratospheric intrusions on ozone at these high elevation sites. For example, have you seen high ozone events characterized by low CO or low ethane in your data sets? Thank you.
Yeah, so we also have the good observations of the ozone sonde. So we also see the good amount of the downward transport event at our site because of the subtropical jets and all. So yes, we observed, but simultaneously we didn't see because we only have some observations of the ozone along with the radio sonde. Yeah, but we see the downward transport event at our site and which influence ozone also.
Okay, thank you. Any other questions from the audience?
I have a quick question, if I can.
Yeah, go ahead.
Yeah, I'm curious. This may not be super relevant, but I see your observational period is pretty long and covers some of the very severe heat wave periods in India. I'm curious, like, do you see any signals in your mountainside observations that is like associated with this heat wave? Do you see any differences?
Actually, the primary objective of this study is just to characterize and present the observation results. In the next, now what we have doing, we have the good number of the data sets from the almost 20 to 15 to 20 years of the data samples. So then we are looking for the such kind of the changes, because if you go for the heat wave and all, the Himalaya region is not that much prone to that heat waves. The altitude of that site is almost 2000 meters from the sea levels. So the site is not that much affected. But if in terms of the talking, in terms of the transport and all, the challenge is that in the foothills also you can see the levels of hydrocarbon is quite high. So if we want to quantify, then we need a good number of analysis and models also. So yes, it's good to look into that perspective also. Thank you.
Thank you.
All right, thank you. For the matter of time, we have to move on to the second speaker, Bing Luo from Shandong University. And Bing Luo is a PhD candidate at Shandong University, supervised by Dr. Jianhao Zhang, focusing on the spatial and temporal distributions of global and regional atmospheric pollutants using the NCAR-CESM2 model. And the titles of her talk today is Impacts of Regional Anthropogenic Emission Change on Global Tropospheric Ozone Burden from 2000 to 2019. Welcome, Bing Luo.
Thank you. Now I will show my. Oh, maybe need to describe the last show, the last screen.
Can you share your screen?
I need to the last one to disturb his screen.
And could you stop sharing first?
Oh, Mahendar, can you stop sharing? Okay, I think it seems working.
Means
Oh, you have, okay, yeah.
There
I
is
see.
I'm not sharing anything.
Okay, I think Bing Luo's screen is starting up. Yeah, we see it.
Okay.
Yep, go ahead.
Okay, thank you. Hello, everyone. I'm Bing Luo, and I'm a PhD candidate from Shandong University. Today, I'm honored to be here to introduce our recent work titled Impacts of Regional Anthropogenic Emission Changes on Global Tropospheric Ozone Burden from 2000 to 2019. So, tropospheric ozone is a powerful greenhouse gas and air pollutant that hurts human health and ecosystems. From the observation and the model simulation, both concepts show that tropospheric ozone increased across most of the globe, particularly over India, China, and Indonesia. So, what drive the global tropospheric ozone burden trade? So, the formation of tropospheric ozone is affected by anthropogenic emission and biogenic emission, as well as meteorological conditions. So from the Purell study, we can see that the increased green area means indicates that changes in global anthropogenic emission are the main drivers of the increase in global tropospheric ozone burden. So anthropogenic emission changed in different regions over 3 decades, from the 2000 to 2010. There is an increase in rapidly developing regions like Asia, and a decline occurred in parts of North America and Europe. But from the 2010 to 2019, substantial reduction of anthropogenic NOx emission occurred in eastern China due to the clean air action in China. So the goal of our study is to quantify the impact of global and the regional anthropogenic emission changes on global tropospheric ozone burden. We use the ChemCam, a state-of-the-art global chemistry model, and all simulations are conducted for 5 years from 2014 to 2019, and after speeding up for 1 year. And the anthropogenic emission are from sets with make used for China. Biomass burning emissions are from campsite Q5 and fan. Biogenic emissions are calculated by using Megan. And we set base simulations for 2019, and we set another age sensitivity simulations. And in these simulations, we set global or 3 regional, like East Asia, South Asia, and Southeast Asia's anthropogenic emissions in 2000 or to 2010. And for all simulations, biomass burning emission fixed as 2019, and the results are presented as 5-year average to isolate effect of climate variability and change. By comparing these simulations, we can quantify the impact of anthropogenic emission change, like the difference between base and the fixed global 2000s represents the impacts of global anthropogenic emission change from 2000 to 2019, and the difference between base and the fixed global 2010 represents the impacts of change from 2000 to 2010, and the difference between fixed global 2010 to and fixed global 2000s represents the impacts of emission changes from 2000 to 2010. So we also evaluate our model performance by using MLPITT-CO. We can see that there is a small bias between our model with the MLPITT with under-restricted rates over the northern hemisphere. when compared with OMIMEL's tropospheric column ozone. And our model can reproduce the spatial pattern of tropospheric ozone burden, and they are still underestimated about 90 TG. So, for global tropospheric ozone burden estimated by our model within the range of the 8 CMAP6 models simulation results. When compared with the ozone sound, a coefficient exceeding 0.8 and the difference from the mean typically within the 25%. Next, we will discuss our results. Firstly is for global and regional anthropogenic NOx emissions. There are 11 regions followed our previous work identified. We can say that from the 2000 to 2019, the total global anthropogenic NOx emission first increased and then decreased. And for East China, for East Asia, the red one, they first increased and probably driving the increase in the first decades, and then they decreased. And for the blue one and the green one, for the South Asia and the Southeast Asia, they continued increased. And for the developed region like Europe and North America, they still decreased. This figure shows that the annual regional contributions of anthropogenic NOx emissions, and the black line means the contributions from total East Asia, South Asia, and Southeast Asia. It's increased over the time and exceeding 40% of the global total by 2019. So then we next move to discuss the impacts of global and regional anthropogenic emission changes and for the global tropospheric ozone burden. In global anthropogenic emission changes led to an increase by about 11 TG in global tropospheric ozone burden, and we can see that with about 76% of the total increase over the latitude 20 degree north to latitude 30 degrees south. And the increase most pronounced in the first decade while slowing down in the following decades. From the spatially largely ozone burden increased occurred over East Asia, South Asia, and Southeast Asia, and the downwind region. Meanwhile, North America and Europe showed a decline in tropospheric ozone burden. And let's move to the regional anthropogenic emission change impacts. The first line is for the East Asia's impacts. And the impacts of the East Asia's led to an increase to global tropospheric ozone from the 2000 to 2019, and it's largely enhancements in the East China. During the 2010 to 2019, there have been to a decrease for the global tropospheric ozone burden due to the anthropogenic emissions declines as NOx emission we just defined about before. So the impact of East Asia anthropogenic emissions transform from a net positive driver to a net suppressor. And for the another two regions, the South Asia and the South Asia, it's led to an increased increased the trapped ozone burdens over the 2 decades, and the impacts of the South Asia and the South Asia's emissions change show a slowdown between these 2 decades, yet they still remain the dominant contributor to the global tropospheric ozone burdens increase. And for the next, for the radiative forcing of tropospheric ozone burden, for trapped ozone is the third greenhouse gas and exerts a positive radiative forcing. And from the 2000s to 2019, global anthropogenic emission changes resulting in a moderate increased tropospheric ozone radiative forcing, and with the meaning increased over the troposphere region, and with a decrease in the most of north hemisphere, and almost 3 regions. The East Asia's contributed the most significant impacts, exceeding that of the East Asia and South Asia. So to our conclusion, we do discuss the global and regional anthropogenic NOx emission changes, and from the 2 decades global anthropogenic NOx emissions first rose and then
Great.
of global and regional anthropogenic changes from the first decade of global tropospheric ozone burden. The total global anthropogenic emission increased the tropospheric ozone burden of 11.96 TG from 2000 to 2010, and East Asia from a post increased to become a decreased influence in the second decades, and South Asia and South Asia remained the dominant contributor to the global increase. For the radiative forcing, the global anthropogenic emission change results to an increase of the tropospheric ozone radiative forcing, with Southeast Asia has the strongest regional impacts. And that is our word. That's all. And thanks for your attention. And I'm happy to have any question. Thank you.
Thank you, Bing, for the very interesting results. And now we are going to open the floor for questions. Are there any questions from the audience? No? I'm hearing quiet. Okay, I have a question that I just wondering, have you looked into if this model captures the observed surface ozone increase over China during 2014 to 2019 period? I see that your evaluation focus on tropospheric ozone burden, but the main drivers of this increase, for example, over Eastern China is on surface. So I just wonder, have you looked into how well the model captured the observed ozone increase? Thank you.
Oh, thanks for your question. Maybe there will be our next step to more evaluation our model performance. To now we just to evaluate the ozone sound and the tropospheric ozone, and next we will to conduct to do the surface ozone's evaluations.
Okay, we have time for one quick question from the audience. There's questions from the chat.
Okay,
No, I cannot see it.
The first question is for model evaluation. Did you evaluate model? Okay, what's the? Oh.
Okay, I don't see it. Maybe it's not. Okay, we have to move on to the next speaker. Yeah, can you stop sharing?
Yes.
Thank you. Yeah. So
Thank
we have
you.
to move on to the next speaker, Dr. Jianhao Zhang. He is a research scientist at the Cooperative Institute for Research in Environmental Science series at the University of Colorado Boulder, and working in the clouds, aerosol, and the climate group. And his primary research on understanding boundary layer clouds, the atmospheric and microphysical processes governing their behaviors and their relevance for climate. And Dr. Zhang obtained his PhD from the University of Miami and his BS in meteorology from Florida State University. And the titles of his talk today is Detectability of the Large Radiative Forcing from the 2020 Shipping Fuel Regulation and its implications for marine cloud brightening. Welcome, Dr. Zhang.
Thanks for the introduction. Hello, everyone. I'm Jianhao. So as you can see, I kind of chose a little bit intriguing title. This is a title I borrowed from Theo Stein, who wrote a really nice news article for our recent paper. The title is How to Measure the Shades of Clouds That Are No Longer There. So hopefully after the presentation, you'll be able to see the connection between our real title for the paper and this intriguing title. So I want to acknowledge my co-authors, Yaosheng, Chen, Tuck, and Graham. So I'll start by mentioning the health impact of shipping emission to, and as you can see in this figure, there's shipping emission emits pollutants that are associated with premature deaths. That's largely concentrated in these port regions, large cities. So the effort to reduce the shipping emission, the PM concentration is to improve the public health perspective. However, there's another aspect of this problem that the shipping emission also affect our climate through clouds and through direct solar radiation interactions. So this is IPCC figure. As you can see, the shipping emission is in net cooling our planet. This is due to aerosol radiation interactions and aerosol cloud interactions. And one very easy and convincing evidence of this aerosol cloud interaction is the ship tracks that we see observing satellite images. And these bright linear cloud features trailing ocean-going ships. And as you can see that on the right, there's two examples of that. So the science behind the ship tracks is basically there's a so-called Toomey effects where you emit more aerosol into the boundary layer and evacted by the updraft to the cloud base and becomes condensation nuclei competing for the same amount of water, and then creates more smaller droplets that reflects more sunlight. At the same time, some smaller droplets also suppress the precipitation process and then making the clouds can last longer, their lifetime increase, so that they have more time to reflect more sunlight back to the sky, the space. However, if you look at the kind of the IPCC assessment on aerosol cloud interactions, there's a huge error bar here. And this is mainly coming from the uncertainty that we currently have, the techniques, the tools we have in assessing these kind of interactions. And an important issue is the negative cloud adjustment due to smaller droplets. As you can see this figure, there's a huge range of assessment on this. liquid path adjustment, how much liquid water, the change in liquid water after you see the cloud with more aerosol. And in some cases, in this orange color, is actually this adjustment cancel out the Toomey brightening effect. So you're actually getting a darker clouds instead of a brighter clouds. So in order to reduce the uncertainty of aerosol interactions, we really need to work on this cloud, not only the instantaneous Toomey brightening, but also the feedbacks and the longer timescale adjustments. So in 2020, there's a regulation, global regulation from the International Maritime Organization that put a stricter cap of the sulfur emitted from the ship exhaust that goes from 3.5% to 0.5%. So it's about 80% decrease in the sulfur emission from the ship exhaust. This is known as the IMO 2020. So our question is to evaluate or quantify how much radiative forcing does this event produce, and also how much does it contribute to the recent warming trend we see in 2020 and 2023 and 2024. So James Hansen had a recent paper a couple of years ago that shows the evidence that the Earth's radiation imbalance is increasing recently, and you see the radiation reaching the surface as a positive anomaly going upwards. But this is a radiation budget. We don't really know what's contributing to this trend. A recent paper in Science kind of highlight the role of clouds, low-level clouds in particular, is shrinking, and this is letting more radiation into the surface. So this is kind of what we are thinking and kind of hinting at this emission regulation that can, if you think about before you emit aerosol and then the seed clouds make the clouds brighter, but now you reduce aerosol, it makes the cloud darker and reduce the cloud brightness, cloud cover. And so we are trying to look into this. And the issue is aerosol cloud interactions is very nonlinear, and this is a figure from Duncan's paper in 2022 that shows a reduction in the aerosol coming from the sulfur emission. It's an 80% reduction consistent with the regulation, but if you look at the number of ship tracks detected, it's not the same ratio. It's a smaller reduction in the ship tracks. So this hinting at the nonlinearity of the aerosol cloud interactions. And on the other hand, we have a cloud responding to a large-scale meteorological conditions to the first order. As you can see, this figure really nicely show that you see ship tracks in this part of the cloud deck, but on the other hand, on the other side, you don't see it. It's just nature is clearing the clouds because of the meteorological conditions. So we use a machine learning model to capture this first order cloud to meteorological relationship, and then trying to review the effect of emission regulation and estimate this the radiative forcing of this event. So this thinking is kind of very straightforward. This is some synthetic data just to illustrate the idea. So we have let's say a cloud radiative effects time series, really nice annual cycle, and we use the data before 2020, before the regulation took place, to train our model, the neural net ensemble model, to capture this relationship and use this relationship moving forward as creating a counterfactual. This is something like a business as usual scenario. So and then contrasting this with the observed, satellite observed radiative properties of clouds of these years after 2020, we get the radiative forcing. The difference will be the radiative forcing. It's kind of a straightforward thinking, and in some details of the machine learning framework, we have 8 meteorological factors from the aerofab analysis, and there's cloud properties from series models observations. We focus on 2 variables in this presentation. This is cloud radiative effects and the number concentration of the cloud. I'll skip the details, but you can ask me more about the machine learning techniques. So we focus on 3 stratocumulus regions in these 3 boxes, red boxes. They're high concentration of shipping traffic. producing a lot of aerosol sulfur emission, and also they're the three major stratocumulus stacks of the Earth. So this first figure is showing the decrease in number concentration due to this IMO 2020, and then see almost everywhere you see a decrease in droplet number concentration, especially over the Northeast Pacific and Southeast Pacific. And in the Southeast Atlantic, there's a unique feature that really shows up nicely in our approach. Is a shipping lane feature, which is the shipping route in this region is aligning with the prevailing boundary layer wind that's helping concentrating the aerosol emission in a very narrow band of shipping route. So that's why you see a huge signal here. Moving on to the cloud rate effects is more noisier than expected, because we know that aerosol cloud interactions is not just TUMI effects, it's cloud adjustments, the complicated effects. So I won't go into details about why we see this kind of pattern. There's explanations in the paper, but I just want to highlight the overall radial forcing we calculated is about 0.07 watts per meter square due to this event. So to put this into context, we actually compare our estimate with a bunch of other GCM studies that look at the same event, and we are kind of in the same range. But we only focus on the three stratocumulus regions, where the others look at the global regions. So overall, we see about 0.1 watts per meter square due to this event, and this is equivalent to about 3 years of CO2 warming based on the current rate of CO2 warming. Another way to think about this is that if you think about, since the Industrial Revolution, we have about 1 watts per meter square cooling due to aerosol forcing. And this abrupt change in emission regulation actually reversed that by 10% in a single year. So this is a substantial, strong radial forcing. But another question we want to address is this large-scale forcing detectable? So I want to highlight one thinking that there's a significant perturbation due to aerosol change does not necessarily lead to a detectable perturbation against your background natural variability. One example is I just showed that humans' fingerprints and nature's fingerprints easily overwhelm your anthropogenic activities. So in order to assess the detectability of this event, we kind of quantify this by true detection versus false detection. So for example, a false detection could be a detected perturbation. Let's say after 2020, we see a significant change compared to before 2020. And this could due to a meteorological shift in the boundary layer conditions that lead to a significant change in cloud rate effects. It had nothing to do with aerosol perturbations. On the other hand, we can have a significant aerosol-induced perturbation, but the meteorology is driving in the other direction that lead to an undetected perturbation. So this is your misdetection scenario. Here is the diagram that we use to show a quantified detectability. So on the y-axis is true detection rate, and x-axis is false detection rate. So a perfect detectability will be 100% true detection and no false detection. And detectability increase in this diagonally way, and this one-to-one line is basically the equal chance of true detection versus false detection. So having this in mind, we put our results here. So let's look at the cloud rate effects. So the colors here, different dots indicates different regions, the stratocumulus regions, and overall you see everything is kind of below the 50-50 chance. So meaning there's an equal chance of detecting a true detection and a false detection. Indicating there's an overall low detectability of this event. This is because cloud rate effects is really if you think about detection, it's signal to noise ratio problem. And this is highlighting the noise of cloud rate effects is really high that overwhelm this even a strong signal. On the other hand, if you look at the left figure, the microphysical perspective is there's a higher detectability for the macrophysical properties, and this is because of course the noise is smaller for the macrophysical properties.
Okay,
so
you have 30
to
seconds
summarize,
to wrap up. Yeah.
Yes, so summarize, I just want to highlight two kind of implications of this work. One is that if we continue this kind of cleanup efforts, reduce our aerosol emission, we kind of expect to have accelerated greenhouse warming in the future, and this could also lead to drier soil. That's conditions for forest fires. And for marine cloud brightening experiments, we will need to exceed more aerosol to overcome this general low detectability of cloud-related effects. And thank you, and happy to take any questions.
Any questions from the audience? No? Well, while everyone is thinking, I have a quick question. So you know that the climate models typically have difficulty simulating marine stratus clouds in the California, Peru, and other eastern boundary current regions that you show have the biggest impacts from the shipping emissions. So I just wonder, do you think that if we do these perturbation simulations with climate models, do you see we can see these signals in climate models?
So this plot actually shows, so our work is the first one, and all of them are GCM simulations of this event. So I mean, you made a good point that too few problem of low cloud stack, but still they given what they have, the macrophysical parameterization they have, this is what they produced, and it's kind of in agreement with each other. So I think it's still with a range of uncertainties, it's still something we learned from this event, about 0.1 parts per meter square.
Okay, are there any questions from the audience? We have.
Hello, I have a question.
Yeah.
Regarding your machine learning method, I was wondering, maybe here you have an assumption that these input features will not be affected by this IMO regulation, right? To create these counterfactual results. So I was just wondering how valid this assumption is.
Okay, so that's a very good point. So your argument is basically after 2020, the aerosol changes could induce large-scale circulation traces that's also changing the predictors.
Yes.
So we actually we haven't tested that, but definitely that's something could be happening. So in GCM simulations, what they did is really they nudged kind of the wind patterns in overall. So they also don't address this question directly. For machine learning technique, yeah, we just have to assume. I mean, it's an attribution problem. Is some people attribute like the aerosol forcing directly just aerosol cloud interactions, but some people attribute aerosol forcing including those large-scale circulation changes. So yeah, good point. Thanks.
Okay, thank you.
Okay, since we start late, I think we can have 1 more minute. If there's questions to all of the speakers. Okay, I'm hearing none. So I'm return the seminar to the early career committee. Are there any announcements you want to make before we adjourn? Christian?
Yeah, just I posted the links in the chat if anyone from the audience is interested in submitting an abstract to present here. And yeah, you can also email us with any questions or feedbacks. Yeah, or if you want to get in contact with today's speakers, if any question comes up. And yeah, it would be great if you're fill out this survey about today's seminar. Yeah, but that's all we have.
Okay, let's thank all of the speakers for their presentations. All right, that's it. Bye-bye.